Are you ready? So this is what I slogged you through all this chemistry for. Put it all together, right? Putting it all together here. All together now. So this matches a diagram in your textbook. I think it's a great diagram. I don't think it makes a lot of sense until someone actually talks you through it. So here, this is basically the fast carbon cycle, right? This is the atmosphere, land, ocean, and if we total all of that up, we get about 46,000 gigatons carbon. Most of that's actually in the deep ocean, if we remember. And then over here, we've been talking about rocks, the slow carbon cycle. And again, just to remind ourselves of what these numbers are and our goals here. So we have a flux of slow carbon into the fast carbon cycle of about 0.1 gigaton carbon. Now, let's all rewind in our brains and think, wait, if we know how much carbon is in the fast carbon cycle, and we know the rate of flux of the slow carbon cycle, we can figure out a residence time. We can actually just do the math, right? You take the total in the reservoir and the flux, and you see how that works out. Simple, right? Yeah, this is like third grade math, which is division. Or rates, I guess. So if we look at 46,000 gigatons of carbon and 0.1 gigaton carbon per year, turns out the gigatons cancel. And if we look at the residence time in the slow carbon cycle, it's actually about 500,000 years. So just shy of 500,000 years. That's long. And now we're going to hopefully be able to see how we can mess this all up, right? Now is our chance, right? Now we can come in here and start messing with some of these numbers. So the first thing that we need to talk about is all of that carbon that's stored over here in the rocks. We talked about limestone, we talked about kind of oil shale or shale that has a high organic content, and coal. And essentially what we've done is we take that material, that high carbon combustible material, and we pull it out of the earth and we burn it or we combust it for energy. That chemical reaction is actually one you've seen before, although in a different context. So here's our combustion reaction. We've got carbohydrates, whether they're kind of long chain alkanes. You could think about CH4, that's methane. Octane is CH832, off the top of my head. But carbon and hydrogen, these carbohydrates oxidize, and that forms CO2, H2O, and actually the byproduct is energy, very similar to respiration. So this is the combustion reaction that's happening in your engine, that's happening at a coal-fired power plant. Anytime we're burning carbon, we have CO2 produced, we have energy, and also water. So hopefully it doesn't take you too much to realize we've now taken long carbon, right? Long cycle carbon with a residence time of about 500,000 years, 500,000 years on average, and we've actually pulled it out and added it directly to the atmosphere rather than letting that process play itself out. So this number actually increases every year. Some of the data that I was using before was a little bit out of date, but thinking about the carbon that we're adding, we've actually now taken this, and we're actually adding about 8 gigatons of carbon per year from the slow carbon cycle, right? We're pulling it out and actually adding it directly to the atmosphere, and the atmosphere can't react that quickly, right? So remember, I mean, part of it, respiration and photosynthesis, has a fairly short residence time, but that can get overwhelmed. The deep ocean, where most of it is stored, has a residence time of hundreds of years, right? So a slug of carbon could take hundreds and thousands of years to ultimately end up being stored in the deep ocean. So this big slug of carbon, it's going to be there, right? And then the heat associated with that slug of carbon is also going to be there for a while, right? So you're right, in the long term, this should strip out that excess carbon, but that might take 100,000 years or so to do. Again, the other thing that I wanted to talk about here is something that we touched on the last time, which is actually land use. And so remember that we've got 120 gigatons of carbon stripped out by photosynthesis. But one of the things that we're experiencing is massive deforestation, particularly in heavily forested areas like the tropics. And we are taking those trees, stripping them out for logging purposes, but also to open land for agriculture. That decreases the ability of photosynthesis to act as a sink, right? It pulls less carbon out of the atmosphere because there's literally less biosphere. So we see this happen in an annual cycle, right, with the seasonality when plants are growing and plants are dying. But here, we're actually getting rid of plants, and in most cases, we're burning them, so that CO2 is going straight into the atmosphere. Kind of a byproduct of that is also soil. Right? Soil contains a lot of carbon, but if you don't have trees, you get increased soil erosion. That carbon ultimately ends up out in the oceans, where it kind of diffuses into the seawater. So you can see that by burning fossil fuels and by deforestation alone, right, that's kind of not the end of the story, but those two things alone can throw this whole thing out of whack, and those predict that CO2 levels would rise, right? Because we're adding more, and we're actually impeding our ability to, or we're impeding Earth's ability to strip out the amount that we're adding. So at the end of the day, we know we're adding CO2, we can watch it, right? So we know how much CO2 we're putting into the atmosphere, and we can watch that CO2 when we look at the work of Dave Keeling and these Keeling curves. We can see that CO2, the annual cycles, but the long upward trend. You can see here's this data. We've been collecting that since 1956, I believe. And on top of that, we can actually look at the isotopes of carbon, and we know, carbon has a couple of different isotopes, 12, 13, and 14. Plants preferentially pull out carbon 12, it's the simplest carbon, and when we look at the excess volumes of CO2 produced, they are enriched in carbon 12, more so than the natural kind of ratio, which means the new carbon's coming from plants. Well, there's not more plants that are growing. The plants that the new carbon is coming from are plants that died a long time ago, right? So that's the carbon that's present in essentially oil, coal, and natural gas, right? That is plant-derived carbon, and that's exactly what's being added to the atmosphere. So, again, it's no trick, right? It's actually pretty straightforward, and I kind of thank you for taking this slogging journey through the chemistry, but I do think it's important to really understand the different aspects of the carbon cycle. We did our one overview, and that was great, but now kind of you're really familiar with how all of that interplay works. And what you can also probably imagine is that there's a whole level of intricacy kind of added to that, right? We talked about big brush strokes, big picture, fairly round numbers, but there's even more to it than that. We can start talking about methane, other greenhouse gases that are also affiliated. But for now, I think that we've done a pretty good job. So that'll do it for the week. All right, carbon cycle. Go carbon cycle. All right, I'll see you later.